everyone, today we are going to show you how to design the control loop for dual active bridge in order to regulate the input current. After that, also in this example, we want to design the inductor, the first step after we already tuned the compensator. We save the data points of the current waveform. Then this information we will use in the SmartNetics software. In the SmartNetics software, we try to show you how to design the inductors. After that, as I said, the first step we have to design the inductors with the SmartNetics. Then we try to make a thermal validation uses, for example, Ansys, and the final step is try to make a saturation analysis of the inductor using a PSIM. So the first step, the first software that we want to show you is the SmartCtrl. This is a software in order to design the control loop for any type of power electronics converter. In that case, this is the topology is a dual active bridge. The modulation is in a single phase shift. This is the operating point. As you can see, the input voltage around 175 volts. The output voltage is around 200 volts. The power is 10 kilowatts. The switching frequency 40 kilohertz, the inductance value, and the magnitude that we try to control is the input current. So this is the topology. This is the dual active bridge. As you can see here, we are sensing the input current. Then we have a first order low pass filter in order to attenuate the ripple of the current. Then we try to implement a PI compensator in order to impose the phase shift angles. So in that case, the modulator is based on a single phase shift. As you can see here, we try to control the power flow with the phase shift angle between the gate signal from the primary to the secondary gate signals. The gate signals also are fixed, as you can see here. It's equal to half of switching period. So in this example, in SmartCtrl, we try to measure the plug with the AC sweep function from the PSIM simulator. Then I will save the data point of the frequency response, and I'll import this information in SmartCtrl, and also we try to tune the PI compensator, and in the last step we try to simulate the transient response in order to check if the control is stable or not. So in SmartCtrl, when we open SmartCtrl, the first window that appears is called the initial dialog, this one. And here we have three ways in order to define the converter plan. The first one is the predefined topology. In the predefined topology, you can see different type of converters for DC-DC converter with a single or double loop, and also you can find for the peak current mode control. And in the rectifier, you can find two different options for the single phase PFC and also for the three phase PFC. The second way in order to design the control loops is that I'll use in this example is called the import frequency response data from TXT file. So in that case, I said that the first step, we have to make the AC sweep in the PSIM simulator, and we try to import the frequency response of the converter plan. And in the third way that in SmartCtrl you can define is called if you can define the converter plan, is called the equation editor. In that case, you can write your own transfer function in an analytical way in order to tune the compensator. So let me open the PSIM simulator. This is the dual active bridge. Let me run this simulation. Now it's running in open loop. As you can see here, we have the modulator. This is the phase shift modulator. In that case, we are taking into account some dead time. and this is the switching frequency of the modulator. So in that case, I set a static value of the phase shift, as you can see here. And also we are measure the input current. This is the magnitude that we try to control. And as you can see here, this is the first order low pass filter. The crossover frequency is around 5 kilohertz. Let me open the waveforms. This is the current through the AC inductor or the leakage inductor. And also this is the input current. As you can see, the input current is around 58 amperes. So in the first step, in order to measure the AC sweep, we have to inject a perturbation. So in that case, I try to inject the perturbation in the phase shift angle. In that case, I put here a sine source. I have to change the name, this sine 1, and the peak amplitude equal to 0, frequency equal to 0. So after that, I have to put the AC sweep proof. In that case, I go to elements, to others, proof, and here you can find the AC sweep proof. So in that case, the AC sweep proof I put in the input current measure. So and now it's time to add the AC sweep series block. So in that case, I try to use the multi-sign AC sweep function. If you double click here, you can define the start frequency. In that case, is equal to 50 hertz. The end frequency it's equal to 10 kilohertz. Remember that the switching frequency of this example is around 40 kilohertz. So the Nyquist criterion said that the average model it's accurate until half of the switching frequency. That is the reason that I set a little bit lower than the half of the switching frequency. Then this is the number of the points, and also we have to set the amplitude of the perturbation. So in that case, I set a value equal to 5 millivolts. And also here in the AC sweep multi-sign function, we have to define the steady state time. So in that case, if you can see here, the current achieved the steady state operation around 5 milliseconds. So in that case, I try to put here 10 milliseconds. So now it's time to run the simulation. And here you can see that we have two AC inductance because one of them represents the leakage inductor of the transformer. And in some case, in order to achieve the zero voltage switching, you have to add an additional inductor. So in that case, we have an additional inductor equal to 7.5 microhertz, and this is the leakage inductor of the transformer. So we have to wait some seconds. As you can see here, this is the frequency response of the current plan. So now it's time to save this information. I'll go to click on File, no, Edit, View Data Point, File, Save As. And here I set a name. This is the current plan. I save this information as extension with a TXT file. Click on Save. Now I closed this window. Now I open the SmartCtrl, and I said before we have to go to the import frequency response data from TXT file. Click on this option, and here you have to select if you want to implement a voltage mode control or a current mode control. In this example, we try to implement a current mode control. So click on OK. Here in this window, you have to import the current plan. So in that case, we are selecting the TXT file that I saved before, this one. Click on Open. As you can see here, this is the frequency response. And here you have to define the operating point current. In that case, it's around 58 amperes. And the switching frequency is equal to 40 kilohertz. So after that, you have to click on OK. This is the next window that appears, and here is the design flow of the control structure. Then we have to define the sensor stage. So in the sensor stage, in that case, I have to define a gain equal to 1 because in the AC sweep, the frequency response that I made with the AC sweep already take into account the sensor stage, as you can see here, because I put the proof after the low pass filter. So in that case, I have to select, for example, current sensor, and I can set one gain equal to 1 for the current sensor. Because if I put a low pass filter here, I take into account twice the transfer function. So after that, I have to click OK. Then I have to select the PI, the type of compensator. In the predefined compensator, you can find the type 2, type 3, the PI, and also you can define your own transfer function for the compensator if you select the equation editor. In this example, I try to tune the PI compensator. And here in this window, we have to define the valley value and the peak value. In Smart Control, in order to define a gain equal to 1, because already the AC sweep take into account the gain of the modulator, in this case, so we have to define a gain of the modulator equal to 1. In order to define that, we have to set a peak value equal to 1, a valley value equal to 0, and the rise time of the carrier signal equal to the switching period. So this is the expression that Smart Control estimate the gain of the modulator. So in that case, if you set this value, the Smart Control contemplate that the modulator gain is equal to 1. So in that case, I set 1, value equal to 0, and the rise time equal to 25 microseconds. So click on OK. And now this is the solution maps. In the solution maps, represent the relationship between the crossover frequency in the x-axis and with the phase margin in the y-axis, as you can see here. And all the white region is all the solution that will ensure that the Smart Control ensure that your control will be stable. So we have to select one point for the crossover frequency and phase margin, click on OK. After that, we have to click on OK. So as you can see here, this is the body plots. This is the magnitude and the phase. And also you can move the cursor through the solution map. As you can see here, all the plots in Smart Control are updated immediately. So another thing, you can also define the crossover frequency and the phase margin manually. If you set, for example, here 1 kilohertz, and also the phase margin equal to 100 degrees, for example. So in that case, this is the parameters that we have to copy in the PSIM simulation. This is the proportional constant and the time constant of the PI compensator. So in that case, I have to open again the simulation. I have to erase this part, and I have to add a PI compensator here. So this is the PI compensator, and also we have to calculate the error here. This is the error. We have to add the label of the current sensed current. Sorry, you can put here, and also we have to add the reference. So this is the current reference. So I said before, this is a 58 amperes. And also I want to add a step, for example, 2 more amperes after 15 milliseconds. this is the reference current, for example, E-ref. Here, we have to eliminate the AC sweep settings blocks and also the AC sweep proof. So, and here in the PI compensator, we have to define the gain that I said before. This is the value 3.352 miles. And also in the time constant, we have to define 78 micros. So after that, we can run the simulation. We have to wait some seconds, and in this simulation, we try to check if the solution that we select in the smart contract is stable or not. So let me, okay, current flux, okay. So we have to wait some seconds. Okay, so as you can see here, the input current achieved the reference. In the blue trace, you can see the reference, and the red trace is the sensed current. So as you can see here, and also in the step, the input current achieved the reference. Let me see the phase shift angle. The phase shift angle is not saturated; it's in range. So this is is inside the span. And also you can see here, for example, the waveform of the primary bridge and the secondary bridge, for example. As you can see here, this is the simple phase shift. We are controlling the power flow through the phase shift angle, as you can see here. And the final step is I try to save the waveforms of the current. So let me. This is the current that I have to save if the leakage in current or the additional inductor currents from the AC. Let me eliminate this screen and also this screen. And here we try to select one switching period, for example, maybe here, in order to use this waveform in the SmartNetics software in order to design the inductance. So, for example, I have one switching period. I go again to edit, view data point, select file, save as, and here you have to select the extension with the CSV. So the comma separate file. So in that case, for example, I save the inductance currents. Save. And now with this information, you can use the SmartNetics software.
First, just to explain a little bit the workflow I'm going to have today. The workflow in SmartNetics for design of a magnetic component is you have to input the minimum amount of data you need. You can configure what you want and what you don't want in your design. Then you can design a number of components, you select one, and then you can analyze and export it to third-party tools, okay? This is usually an iterative process. So you design something, you see it's not what you really wanted, so you change the input data, etc. And this is the workflow we're going to follow today. With a small change to what we have done in other webinars, that is, instead of defining a random current or a generic current, in this case, instead of doing that, what I'm going to do is I'm going to use as input the current that Diego has shown a moment ago. Okay, so for that, the same current file that Diego has exported is the one I'm going to use as input in SmartNetics. Okay, so I go to SmartNetics. This is the first screen you see when opening SmartNetics. You can see that you can select if you want to make a transformer or an inductor. For the transformer, you have to provide voltage and current and the turn ratio. For the inductor, only the current and the inductance. So, as Diego used in the simulation, I'm going to design a 7.5 microhenries inductance. And as I have just said, instead of using a sinusoidal or angular current, anything like that, I will load the file that Diego has just generated, the inductor current. Okay? Then, once you have the input data available in here, you have to configure what you want and what you don't want in your designer. For example, you can change what to take into account from the databases. In this case, the cost geometries I'm going to leave as they are. The core materials, I'm going to change something because I want to highlight something that we have added in this release, which is the saturation when exporting. So I'm going to select one of the devices for which we have the points of the VH curves, this, for example. And for the conductors, you have lead wires, rigid wires, rectangular wires, etc. I'm going to leave this rigid wire as it is one of the options. But since the current is so high, I will use a bigger wire instead of the default one. Okay? With that, we have already configured the databases. You can modify everything related to the device parts you want. We have covered that in other webinars. And lastly, you can modify what models to use. Okay? In SmartNetics, we have implemented many models for the different parts of the calculations. If you go to the help menu in here, you can see the description of what we have done. For example, if we want to change the models in the losses, for example, you can see that we have implemented different core loss modes. Okay, so you can select the one that you prefer, the statement one, the modified statement, the generalized statement. In general, the default ones are great for most designs, but you can change them if you want. For example, for the lead wire losses, if you want to use a model specifically designed for lead wire, you can change it. You can do the same for inductance, and you can do the same for the thermal models. You can choose whether or not you want to calculate the temperature. And in this new release, we have included this option in here, which is fan cooling. Okay, so instead of natural convection, you can use forced convection. Okay, so I will activate it and just use the default fan. Okay, with this, you can proceed to the important step in here, which is design. Okay, as you can see, the first time this is empty until you press in here begin magnetic design. Once you press in that, as you can see, we are following a different approach to other tools we see in the market. Okay, instead of providing a single result, a single black box result that you can say, okay, sometimes I need the one with the lowest losses. Sometimes I want the one with the lowest volume or the highest efficiency or whatever. We know that in many projects, there's not a so straightforward solution. Okay, sometimes you want the lowest losses, or sometimes you want something in between. Okay, or sometimes you have to take into account the manufacturability or the availability of the components, etc. Okay, so what we're doing here is instead of providing a single one, we provide every possible combination of the parameters in the database that provide valid solutions. Okay, so that provide every point in these graphs is a design that achieves the design inductance, that can handle that current, that has a temperature below the maximum imposed, etc. Okay, once you have designed all of those devices, you can take a look at up to 8 variables at the same time. Okay, because we have 4 axes, and you can select any variable that has any impact in the design. For example, instead of cost, you can see, I don't know, the length of the gap, for example, the air gap, because it may be important for you. Then, once you have all the variables selected, you can click and drag on any of the plots to select some devices that are interesting for you. And when you select them, the same devices are highlighted in every other axis. Okay, so you can see the impact of any variable on the other ones. For example, in here, I can use a bigger volume, so I will select the devices with 2 cores stacked in parallel. Let's say these ones. And you can see the impact on every graph. And then from these devices, I can say, okay, I can make a device with low temperature, but a very high volume, or a low volume, but very high temperature, or something in between. So for this particular design, I'm going to select the something in between. And let's say all of these designs, which are 8 or 10 or something like that, they are all more or less the same, more or less same volume, more or less same temperature. So all of them are okay for me, more or less. The next step is, okay, from those, let's select the one I really want to design or to manufacture. And you can do that in the next step, which is selection. In here, instead of a graphical comparison, you have a numerical comparison of all the designs that you have selected. And here is when you can really see the impact of some decisions. For example, as you can see, they are all using the same core, the same numbers of core stacked in parallel, etc. But one of the differences is that some of them use a lead wire and some of them use a rigid wire, which has an impact on the wire losses, obviously. The rigid wire has losses that are higher in general than the lead wire due to the AC losses. So for this design, I'm going to keep the lead wire. And then inside the options for the lead wire, you can see that there are many ways to use that wire. For example, you can have 4 wires in parallel, 2 by 2 or 4 by 1. You can have only 3 wires in parallel, 3 by 1, or 2 wires with different combinations. That also has an impact on the losses. The lower the number of wires, the lower the wire loss. So to keep the losses as low as possible, I'm going to select the 2 ones that have 4 wires in parallel, 2 by 2 or 4 by 1. To explain this a little bit, I'm going to open the help menu again, just so I can explain what I mean here. When you are paralleling conductors, if you have a number of wires in parallel, there are many ways to stack those wires. For example, if you are using 6 wires, you can do something like this, something very horizontal, something like this, very vertical, or something closer to a rectangle. This has an impact on everything because the length of the wire is different, the AC losses are different because proximity losses are different, the stray capacitance is different, etc. Okay? For this particular design, I know that something like this, which is something very horizontal, is much more difficult to manufacture than something like this. So this device is going to be much harder to manufacture than this one. Okay, so I will select this one. This can highlight, I think, very easily the perks of doing this kind of design when we provide every possible combination. Because if you just use a function that says, okay, I only want the one with the lowest losses. The one with the lowest losses is this one, the one that is hard to manufacture. And if you take a look at the total loss, the difference, which is, in here, the difference is 0.1 watts. So in reality, that's no difference. So if you just take the one with the lowest losses, you will be saving only 0.1 watts in losses, which is nothing. And in exchange, you are designing a device that is way harder to manufacture. Okay, so it makes no sense for us. Okay, so this is the reason we provide all the information and then the user can select. Okay, if you want to save on losses, you can do that, but otherwise you can select something that is more convenient for you. So this is the one I'm going to select. Okay, once I selected a device, it is reproducing here at the bottom, and you have access to the last step, which is device in here. Okay, in here you can see the details of the device that you have selected. So the geometry, for example, the dimensions of the core and the wire, how it is going to be stacked, etc. The performance, so you can see the temperature distribution, the temperature at the center of the core, at the top and bottom, at the winding, etc. The temperature in just 5 points. The distribution of losses, weight, and cost between core and winding, etc. If you like what you have designed and you think this is good enough, you can also create a report of your device. And in that report, you can include the information you want. For example, let's say for the sales people, you want some information. For the engineers, you want other information. For the people that is going to buy the components, you need another information. So you can choose what to include and what not to include in your report. And then once you press in here, you get a wait bar, and then the PDF is going to be automatically generated. I'm just going to wait a couple of seconds before it finishes, because it's including all the information in that. Okay, so in here you can see the geometry, the same geometry you saw in the application, the main performance parameters, so inductance, losses, weight, price, etc. the temperature distribution. You can also see the manufacturing parameters, so what geometry to use, what material to use, the number of components to buy, so you need this amount of cost, these meters or kilograms of wire, etc. Okay? Thanks to this, you have already designed hundreds or thousands of devices and selected the one that is the best for you. And up to this point, everything has been done analytically, which allows us to do those hundreds or thousands of designs. But in here, we provide another step, which is how to export your design to third-party tools, which is what I want to showcase today, to validate your design. We have a number of export options in here. One of them, for example, is FEMM. FEMM is a free open source finite element simulator tool, which only allows 2D, and you can run your simulation here. If you press in here, you generate the FEMM description of the same device you have selected in SmartNetics, and then you can send that file to other person. You can simulate that in your computer afterwards, or if you have FEMM already installed, you can press in here, and FEMM is automatically launched. It automatically builds your device, and it reproduces in here the same thing you have selected. Same core, same geometry, same wires, same wire arrangement. Everything is the same you selected in your in SmartNetics. And it automatically builds it, runs the simulation, and generates the report of the values you usually want for this analysis. For example, in this case, you can see the field distribution, sorry. You can see the expected wire losses, 3.04 watts, which are close to what we designed here, which was 3.3, so more or less the same losses. And you can do this analysis very fast because it's a 2D simulation. And the good thing about this is the user doesn't need to know how to operate FEMM or even how to open FEMM. Okay, you just press in launch FEMM and it automatically creates the model, which is something, if you have used FEMM, very tedious to do. It automatically runs the simulation and it automatically gets the results. And you avoid the worst part of finite element tools, which is the learning curve, which is usually very steep. Okay. So thanks to this, you can easily, fast, and for free, because FEMM is free, get an electromagnetic analysis of your device. The next step is, okay, it makes sense electromagnetically, so the losses are expected, the inductance is as expected, etc. The next thing you can check in SmartNetics is the temperature distribution. This is what we are expecting, but this is an analytical model, and we only calculate the temperature in 5 points. What we provide is a way to export that to Ansys-Icepak. Okay? In here, you can select what you want to include in your model. You can select if you want to simulate temperature or voltage and current, etc. And you can do the same thing with it in FEMM. With this, you generate your model. And then, if you have Ansys in here, you can simulate that or launch Ansys automatically with this button. Otherwise, you can just send your model to somebody that has a valid Ansys license, and you can run the simulation in a different computer. Okay. In this case, I have a license because Ansys has provided us a license for these webinars, so I will press in here. And it will do the same thing it did in FEMM, but in this case in 3D. It will replicate the same core geometry, the same material, the same wires, the same bobbin, the same insulation, everything in 3D into Ansys-Icepak. And once again, the good thing about this is the user doesn't need to do anything. You don't have to learn how to create models in Ansys or how to open Ansys even. Everything is done for you. Okay? As you can see, it's automatically exporting everything. Okay? So you have a very accurate description of your device in 3D, including, as I was saying, the insulation, the wires, the fan, in this case, everything. Okay? In this case, this simulation will take longer, so I will not wait for it to finish. What I will do is I will open a simulation that I have already saved in here. Okay, this is the same device I have just designed, but a simulation that was already saved. I will open it. Okay. I will just wait a couple of seconds until it opens. Okay, and as you can see, once again, you don't need to learn how to operate Ansys. Everything is created for you, even the reports. The temperature reports are already created for the temperature in different axes, in different axes. So just have to double click and open the results. Okay. I will change I will rotate the device just so we can see. Okay. So thanks to this, you can have a very accurate 3D simulation of your device. And you can see the real distribution of the temperature in your device, including a fan, including the insulation, etc. Okay, I can compare that, with the ones we have in SmartNetics. Okay, and as you can see, we were expecting 71.8 degrees and the maximum temperature. In Ansys, we were 75, so like 3 degrees, 3.5 degrees of difference, which is something great. And the good thing about this is you can use SmartNetics to generate hundreds or thousands of designs in seconds. And then for the one you select, or the couple of ones you select, you can run a very accurate finite element simulation. Once again, without knowing anything about it. Okay? Thanks to this, you can validate, as I was saying, the temperature distribution and the electromagnetic behavior of your device. And there's a last step, which is, okay, I know how to make my inductor. I know my inductor is going to operate as expected, but how is it going to impact the circuit I am designing? So for that, in this release, we have included the last export option in here, which is PSIM. In here, you can select how to export your inductor. I will open the help menu again, because in PSIM there are different ways to define an inductance. You have an ideal inductor, a saturable inductor, etc. Some ways. In this case, I'm going to export a saturable inductor. Okay, just to check if my inductor is going to saturate or not at the real current this dual active bridge is going to handle. You can do the same thing we did before. You can generate the model, and then if you have PSIM in here, you can launch PSIM. Otherwise, you can send your model to someone else or run the simulation in another time or whatever you want to do. Okay. Diego, if you have PSIM open, please close it just in case the license.
Already closed the PSIM.
Okay. Okay, so as you can see, we have already exported our device to PSIM. Okay, everything is included in here, and the good thing is everything related to the saturation, which is this way defined in PSIM, is already done for you, which is something, once again, very tedious, because you have to define the points of current versus inductance for a huge amount of points. Okay, but you don't have to do anything. You just press on export, and that's it. And then this is just your inductance, but what you can do is you can open your design. I'm going to open the same circuit Diego showed before, which is this one, the dual active bridge, and I can copy my device and paste it in here. Okay, because all the information is included in here. And then I can connect it to my circuit. Thanks to this, you can deactivate the ideal and simulate with the saturable inductor, or the other way around. Then once you press in simulate circuit, you can see the results. Instead of waiting for the simulation, once again, I have already saved the results, so I will just open them. I will merge both designs, and I will compare the inductor, the current in the inductor, if you use an ideal one or if you use a saturable one. I will make this a little bit bigger, just so you can see that, and I will zoom in. Okay, and as you can see, as I was expecting, there is no difference. Why? Because as you can see, we have designed an inductor that is not going to saturate in this operation point, because we have designed the inductor for this operation point. But the interesting thing here is not in this operation point. Is let's say what will happen in your circuit if you increase the power. Okay, let's say I change my reference, and instead of going for the nominal power, I go to something that is twice that power. If I run the simulation with the ideal inductor, nothing will happen, because an ideal inductor can handle millions of amps if I want. but that's not what is really going to happen in the real world. In the real world, if you increase the current in your circuit, something is going to change. So what you can do is you can simulate with the saturable inductor. Once again, I already have those data, so I will open the simulation results. And I will compare the ideal versus the saturable. I will make this bigger again. And I will zoom in. Okay, and in here, you can see what is really going to happen. If you use an ideal inductor, the shape of the current is going to be the same as it was before. Because this is ideal, and the inductance is going to be the same if you have 100 amps or 200 amps, as in this case, or 1 million amps. But in the real world, if you use an inductor that was designed for 100 amps, and you increase that current, at some point you're going to start saturating that. And that is what you can see if you include the saturation model that we have provided, which is the red line in here. As you can see, at low current, you are not saturating, so everything is okay. The inductance is the same as the ideal. But once you get to some point in here, your inductance starts decreasing and your slope so increases, okay? And thanks to this, you can see the real current you are going to have in your dual active bridge, which is not 200 is whatever it is, 220 or whatever. So thanks to this, you can really predict what you're going to expect in your dual active bridge. And you can design your controllers or your sensors or your protections accordingly to what you are really going to see, okay? Because the real inductor in the real world is going to saturate, okay? So just to summarize what we have done, thanks to this combination of softwares, you can design your dual active bridge, design your controller for your dual active bridge or for any converter. And then in SmartNetics, you can design your device, you can validate your device against third-party tools, and you can see how your device is really going to impact your circuit. In this case, your dual active bridge, okay? This is what we already do. Just a very brief explanation of what we are including in these tools, because we are constantly upgrading our tools. We are constantly generating new releases of our tools. And in the next release, in the case of magnetics, we're including planar magnetics. So keep in touch for that. And in the next versions, we're going to include more stuff, including exporting to other electrical simulations, just to broaden your options when you want to check the design you have made. Just a little advice in here. In general, in our webinars, you can see what you can do with our tools, but we think that the best way to see that is with a hands-on experience. So you can ask us for trial versions, and we will happily provide trial versions of SmartCtrl or SmartNetics. So you can design some controllers, some magnetics, give it a try, and then if you like, you can always acquire a full license. Okay.